Okay, so in this problem we're given, there's a rotor ride that spins around with people with their backs against the walls. And as it spins, the people stick, air quotes, to the wall. When the floor is pulled from underneath, they don't fall. So our task is to find the coefficient of sag friction that will allow them to stay without dropping. So we have two givens. The radius is 5 meters of the ride and the frequency is 1 revolution per 2 seconds. Now how we're going to start is by drawing a free body diagram. We're going to represent the person with the box. Okay, so and the only force going down is a field force, so that's the force of gravity. And the only force going up is a contact force, a force of friction with the back and the wall. Now there's a normal force too, because that's the second type of contact force that we have to look for, and that's the normal force coming from the wall. Because it's against their back, it points away from the wall, perpendicular to the frictional force and the gravitational force. Okay, now that we have that, we just have to draw in our sign convention to make sure we know which was positive, which direction is negative. Now we're placing the up and to the left as positive in the X and Y direction. Yeah, so it just makes everything easier for us to do.
So to start your sigma F statements, you're going to take the sigma F in the X direction, which will be equal to mass times acceleration in the X direction. And in the X direction, you have the normal force of the wall pressing up against the people, which will be equal to mass times velocity squared over the radius, since that acts as your centripetal force. Then you'll take the sigma F statement in the Y direction, which will be equal to the mass times the acceleration in the Y direction, which will be 0, because the people are not going to be slipping. And the forces you have in the Y direction are the forces of friction and the force of gravity, so you'll have to take the force of friction minus the force of gravity.
Force of friction equals our force of gravity, and force of friction equals mu times normal force. Now we've isolated our normal force equals mg over mu. My political commentary was cut out. Okay, so now we're just going to rewrite our acceleration, our sigma F in the X direction statement. So we know that the normal force equals our centripetal force. And now we can substitute in what we know the normal force is equal to. That's going to be our next step that I'm doing right now. Okay, so now we want to find the velocity. Remember, our frequency of rotation of the ride was given to us, so we can use our velocity equation. And we can plug it into our equation. Oh, and the masses cancel out. Now just getting some space on the board. So after cross multiplying, gravity times radius equals mu times velocity squared. And now let's plug in our velocity. And look at that, we could isolate mu. thus giving us our answer, as you will see in a moment. And plugging that into a calculator, we'll get our final answer, that mu equals now is your time to make an estimate as the suspense builds. So our coefficient of static friction equals 0.19.
The end of the problem asks if there really is an outward force pressing on the person against the wall, and then it asks to describe the situation. This force is a fake force known as the centrifugal force. Due to the inertia and an object's tangential velocity in circular motion, an object will tend to keep moving in a straight line. However, the acceleration that keeps the object in circular motion pulls the person on the ride towards the center. This is the centripetal force, which is provided by the wall that the person is leaning against. That's why the person feels pressed against the wall. But there is no true outward force. This feeling that the person feels is due to the non-inertial reference frame, because they're actually spinning with the system, and they're feeling the wall pushing on them. And this wall is the one that's providing the centripetal force, not an outwards force.